So good morning, everybody. Welcome to the last lecture. And as was to be anticipated, there's a shortage of time, but because I still have 2 chapters left, and in view of this shortage of time, I've now decided to do it a little differently. I will devote most of this time to the subject of supersymmetry, and if there's some time left, I suggest that we leave that for questions. I haven't had any questions during the lecture, but there were questions after the lectures, and maybe if there's time left, you can then ask the remaining questions on all of these topics, and maybe others if you want. So, as I said, I included supersymmetry in this schedule because that's the one subject that is not treated in many of the textbooks. I gave you a list of textbooks yesterday, and the only one which could have it is Ramon's textbook. There I'm not sure, but certainly in the other textbooks you will not find anything about supersymmetry. Weinberg in his introduction says, if I remember correctly, that this is a subject that would require a separate textbook. And of course there are no separate textbooks on supersymmetry. So this is a mini introduction to supersymmetry, and the reason is, of course, as I've already mentioned, that this is becoming very interesting now, also from an experimental point of view, and we're all waiting for some new physics beyond the standard model, and at this time many theorists would guess that if there's physics beyond the standard model, it's going to be supersymmetry. So, this is paragraph number 6. And I have a short historical introduction. Where does supersymmetry come from? Now, supersymmetry grew out of attempts in the 60s to unify space-time symmetries and what's called internal symmetries. So in this lecture we discussed already the space-time symmetries, made the Poincaré group. So that's more or less just the symmetry, and maybe discrete symmetries, of course. But on this side there are many more possibilities. By internal symmetry I mean symmetries like isospin, flavor symmetry, color, flavor, color, what have you. Of course, color wasn't invented in the 60s, but I'm just listing this. We now know that there are all kinds of internal symmetries. Now, the notion internal refers to the fact that here we have a symmetry acting on physical space-time, and here what is meant is that there's some kind of internal space, for example, the space where this isospinner lived in, which I wrote down yesterday, and then these symmetries act as rotation-type symmetries in this internal space. Well, in the 60s there was an attempt. In the 60s, as I said, there were these attempts. And this is just to quote an example what people tried to do. The symmetries that were known were the SU3 symmetries of the Gell-Mann-Zweig quark model. This SU3 of the quark model, flavor. And, well, what other symmetries do we have? Well, we have the Poincaré symmetry, that's of course SO1, 3. But people in those days tried something more modest. They restricted attention to the spin subgroup, SU2 spin. So it's the SO3 subgroup contained in the Lorentz group. And then they had the idea that maybe we can describe, maybe physics is in some sense invariant, or at least approximately invariant, under bigger symmetry. And one symmetry that was attempted was to look at a group, SU6, which unifies these two groups. Now, this initially had some success, but then people said, of course, well, spin is not everything. We also have the boost symmetries. So let's try to enlarge this scheme and to find some bigger unified group that would also describe the full Lorentz symmetry, or would contain it. Well, these attempts failed, and the nail in the coffin to these attempts was a theorem that, due to Coleman and Mandula, it's called the Coleman-Mandula theorem, which states, well, I'm not listing all the technical assumptions. This is a highly technical paper that even would take me even weeks to understand. They really worked through it. But this theorem basically states that this unification of symmetries is not possible within the framework of ordinary within or with ordinary Lie algebras. And the assumptions that went into this theorem were the usual assumptions of relativistic invariance, unitarity, and so on, which I'm not going to list. And what it means is simply that if you have the idea that maybe SU6 is not the right group, so let maybe try something else, something even bigger, this theorem finally states that you can try as long as you want, but you will not succeed. Now, what does ordinary mean here? Ordinary means, well, what is a Lie algebra? A Lie algebra, if you just think about the rotation symmetry or the Poincaré algebra which we had, it consists of a set of operators. Ordinary Lie algebra consists of a set of generators, of a set, and we call them G, and can label them by A, obeying commutation relations, something like GA, GB is equal to some structure constant FABC, GC. An important thing here is that, well, it's kind of obvious that it should be like this, is that what you see here is a commutator. So it's GA, GB minus GB, GA. And all the symmetry algebras that mathematicians had thought of in the decades before were, of course, of this type. When they were talking about Lie algebras, they always meant this. Now, yesterday and the day before yesterday, we talked about fermions. So, to make a long story short, the idea is now to also allow for fermionic symmetry generators. This is typically an idea that no mathematician would have had, because this is something that physicists had to come up with, because of course in physics we're very well used to the notion that there are bosons and there are fermions. We have a spin statistics theorem, and going through quantum field theory like I did, crash course, with the fermions, you're forced at some point when you treat the Dirac field to introduce anti-commutation relations rather than commutation relations, as I tried to explain. So from this point of view, it's perfectly natural to think about something where some symmetry structure, where these commutators are replaced by anti-commutators. Well, now what would that mean? This means that this new kind of symmetry, and we'll refer to it as supersymmetry, will relate particles of different spin and statistics. So symmetry relates particles of different spin and statistics. So at the end of the day, we'll end up with a symmetry that maps or relates a boson field to a fermion field and vice versa. But this is, of course, very unusual. It's also unusual to mathematicians. And one of the funny things we have to do here is that whereas for an ordinary Lie algebra, as I said yesterday, Lie algebras or Lie groups are essentially groups which are continuous in some sense, where you have continuous parameters, and moreover, which are such that almost all the information about the group can be recovered from infinitesimal transformations. You just go to the unity element in group space, you perturb a little, and then you have already all the information about the group. So it means in particular that any group element can be exponentiated, so any element of the group can be written as I to the omega a ta, where this is a rotation parameter. Now in this case we will see that if we have bosonic fermionic generators, then we'll have a similar formula, but it will turn out that the parameter which we have to put here in order to make things work will have to anti-commute. It will be an anti-commuting number. Now, anti-commuting numbers are very unusual. It's certainly not something you can measure. They're very funny numbers called Grassmann numbers. They are formal devices, and although we use them all the time to construct these theories, of course at the end of the day, when you use this theory to make a prediction, you will end up with an ordinary number. You can think of this a little bit like complex numbers, because you don't really see complex numbers in the laboratory. You always measure real numbers, but they're of course a natural part of the formalism. You can't formulate the Schrödinger equation without complex numbers. So this is another unusual feature, so we have to introduce admit anti-commuting numbers, and then we will be able, using this technology, to work out Lagrangians and invariant Lagrangians, or Lagrangians with invariant with respect to this new type of symmetry. Now, to give you a flavor of what this all means physically, I will give you a very simple example. This is a sort of kindergarten example for supersymmetry. Kindergarten example. And this kindergarten example is something called supersymmetric quantum mechanics. And I'm telling you about this because, in a nutshell, this contains all the basic key features of a supersymmetric system. And this is actually something that once you go back to university and teach quantum mechanics, you can even do in your introductory course on quantum mechanics. So what's the kindergarten example of a quantum mechanical system? Well, that's the harmonic oscillator. Harmonic oscillator. And we're now very educated. We use creation and annihilation operators to describe it. So we have a Hamiltonian, and let me put a B here because for bosonic, which is given by, where I discard all the constants which are not essential to this argument. When you learn about this in quantum mechanics, you start with P and Q, and then you introduce these operators, and then you calculate what the Hamiltonian is, and then you find that this is what it is. And furthermore, we have the commutation relation that A with A dagger is equal to 1. And so this is equal to, if I use this commutation relation, it's equal to A dagger A plus 1/2, where this is the 0-point energy. So now we can complement this by corresponding fermionic oscillator. Now, what's a fermionic oscillator? Well, the simplest quantum mechanical, it's really the simplest quantum mechanical system. It's a system of one spin that can point either up or down. And this object can be described by a 2x2 matrix, or alternatively, I can describe it in terms of similar terms, where I write B, B, minus B, B dagger, where now B with B dagger anti-commutes to give 1. Now, I don't want to explain this in terms of matrices because you can look it up in any quantum mechanics textbook, but another way to get these formulas from what we already have is you go back to a lecture of 2 days ago where I gave you the Fourier expansions of the scalar free field and the Dirac field, and remember that in this field we had Fourier modes, A of P and B of P, both for the fermions and the bosons. And what this is really is I just pick out one mode, just one. The quantum field then will be an infinite collection of such modes, and the supersymmetric quantum field theory can be manufactured out of these objects by just giving these things labels like momenta and maybe spin, and then combining them into a field. Okay, now remember this, we also had this plus sign in the scalar quantum field. We got this vacuum energy, and as I told you, if they have infinitely many oscillators, then this factor, the contributions sum up to plus infinity. And this was the first divergence we had encountered in quantum field theory. Now, the same thing, well, there also happened something here, because if I now interchange the order of these two operators using this relation, then I will find it's B dagger B. But now, because of the minus sign here, I get minus 1/2. So it means that, well, I'm sure you've heard this before, because this is something that appears over and over again in physics, that when, also in solid state physics, for example, so when you calculate perturbative corrections, Feynman diagrams, and so on, then you learn that whenever you do have a fermion, there's an extra minus sign associated with every fermionic loop. Well, basically, this is the same kind of minus sign, and you also have the minus sign here, which tells you that the fermions always contribute something negative to the ground state energy, whereas the bosons always give a positive contribution. Well, now we can combine the thing. Now combine this into H boson plus H fermion, and you now see what happens. What happens is that these two contributions cancel. Now here it's almost trivial, but well, it is really trivial. That's why I say it's kindergarten. But this is basically a mechanism that will recur in supersymmetric quantum field theory. Certain things that are there in the generic bosonic quantum field theory or non-supersymmetric quantum field theory, they will cancel in supersymmetric field theories. So this is equal to A dagger A plus B dagger B. And so here we have the first example of a cancellation of, well, in this case not divergences, that's due to supersymmetry. In quantum field theory, as I said, you combine, you have an infinite collection of such objects. Each of these objects will, or each of these terms will contribute something like this. And then you see that if the parameters fit, if the masses of these two particles are the same, and you look at the contribution here to this, you will see that they will cancel again. So this is something that's also true in supersymmetric quantum field theory. We no longer have to worry about vacuum energy because the contributions from the bosons and the fermions will cancel each other. Well, I want to tell you about supersymmetry. Now the reason this new Hamiltonian has the nice properties is that it has a symmetry. And it has a symmetry now with respect to a symmetry generator, which I'm going to write down, namely Q. Q is A dagger B, or AB dagger, A dagger B. And so we have Q dagger is A, B dagger. And we can quickly check, this is back of the envelope, that H commutes with Q and H commutes with Q dagger is equal to 0. Furthermore, we can also check that H can be written as anti-commutator of Q and Q dagger. This is an elementary calculation, and you just use these commutation relations to see this. Now, if we see something like this, where this is the Hamiltonian, and here we have some symmetry generator, like if this were total angular momentum, of course we would say, aha, not only is total angular momentum conserved, but furthermore the system has a symmetry. The Hamiltonian is rotationally invariant. Well, so we simply carry over this definition here, and then we see that we can think of this as being a symmetry generator. But the only new feature here is that this is a fermionic generator. It's no longer bosonic. If I commute two of these things, I will find, first of all, if I commute Q with Q dagger, I get the Hamiltonian. And furthermore, if I anti-commute, and Q with Q and Q dagger with Q dagger, I will find 0. So this is the first example of the SUSY symmetry algebra, supersymmetric algebra. Or you can also look at the spectrum of this theory. That's easy enough. We draw it like this. And make two lines because, well, we all know what the bosonic spectrum looks like. There's essentially a ground state, which is here. Well, I can now really write it like this because there's no contribution to the vacuum energy. And then I can put as many excitations into this state as I want. These are just the harmonic oscillator states. But on top of this, and I have this spin which can point either up or down. And, well, that's just one ground state. But then here we have states with, so here the fermions, which have spin up, say, and here the bosons, which have spin down. So we assign these fermionic states a fermion number. If the spin is down, we assign it the fermion number 0. If it's up, we assign it the fermion number 1. So this is the spectrum. It's just the spectrum of harmonic oscillator doubled up. And what you can now see, we can check it from this Hamiltonian, is that there's a degeneracy which looks like this. And these Q operators, they transport you from here to here or from here to here. And again, we see that the symmetry generators, since they commute with the Hamiltonian, they tell us something about the degeneracy of these states. And the degeneracy is such that each bosonic state has a fermionic partner and vice versa. So you can even work this out in more detail, but this is not my aim here, I hope. But the reason I'm giving this example is that it has all the basic features of a supersymmetric field theory. I mean, first of all, the cancellation of the vacuum energy, and secondly, this degeneracy. For every bosonic state, you have a fermionic state. So in the supersymmetric field theory, If you have a quark, then you also have to give it a fermionic partner, which a bosonic partner, which is then called quark, and so on. And for every gauge particle, you will have a supersymmetric partner, which is called gaugino. Well, and I want to go to something more sophisticated. All we have to do is to make these ideas compatible with relativistic invariance. But we can take the hints from there. This is not, by the way, this is not the way it was discovered historically. Historically, it was discovered by when people tried to write down Lagrangians, keep adding fermions and combining bosons and fermions, tuning the coupling constants, looking at what kinds of interactions you could have, and then trying to write down a set of symmetry transformations, like rotations, that would leave this Lagrangian invariant. At first it looked like it was difficult to do, and there were even papers claiming it was impossible, but in 1973 Wes and Zumino discovered or showed how to do it by writing down for the first time a model in 4 dimensions, a non-trivial model with interactions that had this kind of supersymmetry. Well, one clue to this discovery was that to make it work, you needed the notion of a Majorana spinner. So this was 1973. This was done partly at CERN. Zumino was at CERN those days. You need a Majorana spinner. This is something I have only briefly touched upon so far. What is a Majorana spinner? So this is a little extra footnote. Is a self-conjugate spinner. Meaning a spinner describing a fermion that is equal to its antiparticle. For example, as I mentioned, the neutrino could be of this type, but this couldn't be true for a charged fermion. So if you have an electron is certainly not a Majorana spinner. Now, the mathematical expression of this is that you introduce, given a Dirac spinner, call it psi, you define a charge conjugated spinner, psi c as follows. You define it to be some matrix called charge conjugation matrix. And this matrix has the following property. When you conjugate the gamma matrix with it, you get minus gamma mu transposed. And then we have this spinner psi bar, but this is you have to transpose it in order to make it look like this again. So I put this T here. And where does all this come from? Well, this you can read already in the textbook of Birkin and Drell. When you assume that this spinner obeys the Dirac equation in the presence of an electromagnetic field, you have this term E gamma mu A mu. Then when you look at the same equation for the charge conjugated spinner, it will turn out that you get the same equation except that this has been changed to minus. So this is precisely the operation that inverts the charge and exchanges the particle with the antiparticle. Well, a Majorana spinner is now one for which, let me write it here, for which psi is equal to psi conjugate. And this condition halves the number of spinner components. The Dirac spinner had 4 components to start with, and with this extra condition, I eliminate 2 components. in the expansion, the mode expansion of the Dirac field, which I showed you day before yesterday, you can get to the Dirac, from the Dirac spinor to the Majorana spinor by putting the A and the B equal. So you have A somewhere and B dagger, and then you simply replace the B dagger by A. And then it's a real Majorana spinor. And then you have to use properties of these U of P's and V of P's if you want to check this. But it is true. Well, once we've given this, it's also useful to go to two-component spinors by splitting the four components into pairs of two, and the bases which I've chosen, these look as follows. Here we have psi alpha, where now alpha runs from 1 and 2, and here we have the complex conjugate spinor. In order to indicate that it's complex conjugate, this is just a piece of notation introduced in the 30s. You put the bar in this. This is not the same bar as this one. We should call it phi. Phi. And this is the same as phi alpha complex conjugate. This is in the basis where gamma mu is given by sigma mu, sigma bar mu, where sigma mu, we have four matrices. The first one is the unit matrix 2 by 2, and the last three are just the usual Pauli matrices, and the sigma bar is the same, except that we write minus sigma I. So this is just a piece of notation, because we want to use two-component spinors. And this spinor is now denoted by Q alpha I. Q stands for charge. So this is now a spinorial object which has two indices. And of course then we also need the complex conjugate, which is denoted by like this. So here the bar simply indicates complex conjugation. And this I here is a label that runs from 1 to n. The n, well, at the outset we don't want to specify how many of these supercharges we have, but the important feature is that it is spinorial, and you can really see that this object is spinorial because of the spinor index. And then you may have several of these objects. Well, and as I said, in this work, the algebra is exhibited in a more complicated form, and because they were interested, mainly concerned with writing down non-trivial Lagrangian. But soon thereafter, people sort of abstracted the algebraic structure, and it's the following. So it's the Poincaré algebra. Algebra for P mu and M mu nu. And these obey the same relations as before. So those are the relations of my first lecture. And then, well, I can also take the hints from here. Then I will have to say what does, P with Q, M mu nu with Q, what do the Q's among themselves? And the general scheme is that if I have bosonic operators, I write commutators. If I have fermionic operators, I write anticommutators. And if I have both of them, I write commutator. So it's only when both entries here are fermionic, then I will write an anticommutator. This thing then is what's called a superalgebra, or mathematicians also call these things graded Lie algebras. Okay, so we have the Poincaré algebra and this extra thing. And so we have to specify further relations. Well, Q with Q. As I said, we take the hints from here. The Q with Q and the Q dagger with the Q dagger are taken to commute. So that's 0. But then we have another one which is not 0. And then we take Q alpha I, with one of these, q beta dot j, we get something non-zero, namely 2 delta ij sigma mu alpha beta dot. If you don't understand the dots, just forget them. That's just a piece of notation that can be justified, but would take too long to justify in the remaining 25 minutes. So this is essentially new piece which appears in the algebra. Let me just write one more relation. P mu with q alpha and P mu with q alpha dot I is equal to 0. Well, that's this statement. This in particular will contain the statement that if I put mu equal to 0, that the Hamiltonian of the system will commute with this supersymmetry charge. But also the translation generators will commute with it. I also have relations between mu nu and q alpha I, which I will not write down. They're different from 0, and they simply state that this object transforms really as a spinor under Lorentz boosts. But the relation we're going to concentrate on is this one, because, just look at this, because as you can see, this relation generalizes this relation which we found for the supersymmetric harmonic oscillator. In fact, if you put P mu equal to Hamiltonian and everything else to 0, you get precisely, more or less, you get this relation, except that there are a few more components here. So the really new feature at this point is that we have, first of all, that we've allowed for anti-commuting generators in the algebra, and secondly, that these things anti-commute back into the Poincaré algebra. Now afterwards, through the benefit of hindsight, of course, one realized that it could hardly be anything else. And in fact, there's a theorem stating that this is, in fact, the most general algebra describing a symmetry of the S matrix with supersymmetry. And the only freedom you have here is that you can vary the number of supercharges, this n. And one then speaks about of n extended supersymmetry. Well, the supersymmetry that you hear about when the supersymmetry they're looking for here at Lab and elsewhere, that's always n equals 1 supersymmetry. So phenomenological interest. Interesting is n equals 1. This is the simplest kind of supersymmetry, and that's the kind of supersymmetry we may be able to find at accelerator experiments. Of course, theoretically most interesting is the opposite end. Is n, I don't want to say what it is, but I want to say it's large. Because if it's large, it means the system has even more symmetry. So you see that in some sense, we haven't been able to unify at this point. Well, there's something else I haven't told you about. But here we want to take these space symmetries, eternal symmetries, and have another symmetry. And here we have achieved it, but in a strange way, because we have the internal symmetry is nothing that we know, or have known before, because that's the symmetry of a fermionic nature. But that commutes to something that is into a symmetry which we know, in translation symmetry. So the first first task now is to analyze the possible representations. And this goes back to my first lecture. You proceed in exactly the same way to analyze what are the possible particle multiplets that I can have in this framework. And let's just do n equals 1. So, for example, n equals 1. n equals 1, SUSY means I have only one charge, Q alpha, and its conjugated spinor Q alpha dot. Well, and then in order to analyze the particle multiplets, I do the same as before. I choose a particular frame according to whether the states are massless or massive. And I'll make things simple. I will just look at the massless case. We take P mu to be K 0, 0, K. That is P squared. The idea why this is more important, or the idea behind this, is that somehow the fundamental theory should describe massless particles, and it's only via some effect of spontaneous symmetry breaking that particles get mass. That's also the mechanism in the standard model. You start out with a field theory that is massless, no mass terms to begin with, except in the Higgs sector, and then you have spontaneous symmetry breaking, and all of a sudden your particles get masses. And here one envisages the same kind of mechanism. One has a model, starts with a model. The fundamental model is a massless model, and then there's some symmetry breaking, also supersymmetry, that will give these particles masses. Well, if we now work out what this is, Q alpha and Q beta, now let me write dagger, that's the same as the bar. 2 delta ij, and now I substitute what this is. I remember what this, I have this for 0, a contribution, I have this contribution for mu equals 3. We have said what it is. So it's either 1 or sigma 3. Sigma 3 has 1 and minus 1 on the diagonal. So in one case it adds up, and in the other case it subtract cancels. So we have 2 times, so this is 4k. If I write, this is a 2 by 2 matrix, so I really write out what it is. In this particular frame, where I've diagonalized the momentum operator, so it means that Q1 with Q1 dagger, is commutes to give 4k. So something different from 0, and all others, in particular Q2 with Q2 dagger is equal to 0. So this relation is again, this is the same as this. By going to a special frame and making the assumption that the thing is massless, we get back to this. This is something we understand. Now what's the other thing? Well, that's a little harder to understand what this means. It simply, well, roughly speaking, it means that this operator is practically, for all practical purpose, this operator is equal to 0. In a more technical language, one would say that the states that this operator creates have 0 norm. Now, 0 norm states are unphysical states, you just throw them away. Like longitudinal states for the photon are also 0 norm, and you just throw them away. So of interest in this case for the Hilbert space are only these operators. So here we say that Q2 dagger are, they're not 0 as operators, but they give 0 or 0 norm states. So effectively they're not there, so we can just forget about them. And then we just proceed as before. We start with the state of a certain helicity, and then we apply this operator. And one of the relations, which I haven't written there, the mu nu with Q alpha, tells us that M12, which is the third component of spin, commutes with Q1 to give minus 1 half Q1. So that means that Q1 lowers the spin of the state on which it acts by 1/2 unit. If you put Q1 dagger you will get plus 1/2. Well, there isn't much more because I can now start with a state, start from state lambda. Lambda is some maximum helicity of the multiplet. Could be a photon, can be a graviton, anything. And then we apply the operator, get another state, Q1, lambda, and then this operator will, this will lead us to a state which has helicity 1/2 less. So, what do you have here? Starting from a state of helicity lambda, say the photon, we are forced to introduce another state which has spin 1/2 less. So it's a state of spin 1/2, which is then called photino. And from CPT invariance tells us that if we have lambda and lambda minus 1/2, we also need minus the negative helicity states. So these have to be added. And then what do the multiplets look like? Well, we draw here, we draw the spin. Well, let's say we have spin 2, 3/2, 1, 1/2, and 0. So we can have different multiplets according to where we start. If we start at, say, spin 1, so we have something here, we'll find another state here. Well, now in principle you could try to apply it once more to get a state of yet lower helicity, but if there's just one Q, then we use this relation, and remember that's anti-commutation relations, just states that Q1, Q1 plus Q1, Q1, which is twice Q1 squared, is equal to 0. So if you apply the operator twice, you will not get anything. So there's nothing here. So here we'll find a multiplet with spin 1 and spin 1/2, and this is called a vector multiplet. And if this is a gauge boson, this thing is called a gaugino. So if this is a photon, photino, this is a QCD gluon, then this is a gluino, and so on. Well, we can also start here with spin 1/2, but then we have 1. But then you have to remember that from the other side, we also have the helicity states on this side. We have to add in, and then we get another one. And this is what's called a chiral multiplet, or Mestzumino multiplet sometimes. Mestzumino multiplet, which describes one Majorana fermion and two real scalars or one complex scalar. So there's nothing here. Finally, there's another multiplet which plays a big role, more recent days. If you start from the graviton, you get the state of helicity 3/2, and that's called the gravitino. So here we have graviton, and here we have the gravitino. So this is gaugino. Let's see another piece of. So this is, if this is the particle fermion, then these particles are called fermions. So you have top, stop, bottom, and so on. I find this is not very aesthetically appealing, this kind of nomenclature, but that's what people use. Well, these are the basic building blocks of the so-called MSSM, minimal supersymmetric standard model. Now, the minimal supersymmetric standard model is essentially the standard model without supersymmetry, and you convert everything every particle into a particle multiplet. So you, for every boson, you get the corresponding Gaugino partners. For every fermion, quarks, leptons, you have these fermionic partners. But then there are also these the scalar fields, the Higgses, or really Braut-Englert Higgses, I should say. Then they will have fermionic partners. In a sense, this is not very satisfying because it would have been better, in some sense, if the known particles had fitted into supermultiplets, and there was a chance at some point that the Higgs multiplet and the lepton doublet in the weak interaction theory might fit into one, but then it was shown it didn't work. So this idea didn't work. So you have to introduce separate multiplets for every field that we know. In fact, you have to introduce even more multiplets, and there are many possibilities. This is because this is why it's called minimal. There's a vast class of models here with a vast number of parameters, and it will be quite a difficult task to single out the correct one, if there's a correct one. As I said, we theorists, we are more interested in, we're not so much interested in n equals 1, for reasons other than that these theories might be of interest phenomenologically. We're more interested in large n, because if n becomes larger, you have more symmetry, and the kind of models you can get are more and more tightly restricted. And you can see this if we repeat this kind of construction, but now with several supercharges. For example, if we have 2, 1, and q, 1, 2, we'll get the state lambda, and then we already get 2 states, and then finally we have something like this. So we all have descend by 2 steps in helicity states. So n equals 2 supersymmetry. So for n equals 2, we can write down this table again. Let me just do it for 1, 1/2, 0. So for example, in this case, if we start with a spin with one gauge particle, we'll have 2 fermionic partners. And then here, another one will come in from the other side. We'll have 2 scalars. Well, this is of course rather abstract counting, but what you have to make sure in these theories is that on the mass shelf we count the number of propagating states. There must be an equal number of bosonic and fermionic states. Well, and so on. Now you can go on with yet higher n, and then it turns out if it's clear that if you have more and more Q operators, you cover a wider and wider range of felicities. But we know that nature seems to stop at, nature stops at spin 2, massless. And this implies a bound, namely that n cannot not be bigger than 8. This is what's called the maximal supersymmetric theory. And it's a highly complicated Lagrangian. So I'm almost finished. Let me just say that a few words about the construction of supersymmetric field theories. So far it was just abstract algebra, but let me just write some examples. And these are the supersymmetric field theories of the simplest kind, namely the ones corresponding to the simplest multiplets there are. Namely, first of all, the chiral multiplet, which just has spin 1/2 and spin 0, and then the vector multiplet. Well, the vector multiplet is what you might guess it is. Vector multiplet. The Lagrangian is simply given by the standard Young-Mills Lagrangian, which I wrote down yesterday. And now all we add is I over 2 lambda bar A, and then we have gamma mu, d mu, This is a covariant derivative with respect to this gauge group, lambda, I should write it, B, where now this is, say, an SUN gauge group, and then for every gauge, so the fields are now A mu A, this is the Young-Mills field, and the associated spinor field is the gaugino. And a supersymmetric Lagrangian is the one which I wrote here. And it's already interacting Lagrangian because for Young-Mills we have the 3-gluon and the 4-gluon vertices in here. And here we also have a vertex connecting the gluon with the 2 gluinos. So that's supersymmetric. And if we have the chiral multiplet, we have Lagrangian. As Lagrangian, we have a scalar field. So this. So it's the Dirac-Lagrangian, but for a Majorana spinor, that's also the reason you introduce factors of 1/2. Plus, and then we have d mu A plus d mu B minus 1/2 m squared A squared plus B squared. Well, and then you can add all kinds of interactions. I'm not going to write them down, but you can introduce coupling constants. But the crucial feature here, which is needed to make this supersymmetric, is that the mass of the scalar field, which appears here, and this one, is the same as the one that appears here. So if you put different masses here, then the system will no longer be supersymmetric. And this is the same type of degeneracy that we've seen here in this kindergarten model, namely a degeneracy between bosons and fermions, and we also have this degeneracy here. And the interactions are of a particular type, and it turns out that the coupling constants you can write there are very restricted. The couplings that couple bosons amongst each other and the bosons to the fermions must be restricted in a very special way. And one of the consequences then is that if you have this, if this Lagrangian is supersymmetric, you have cancellation of divergences. So the simplest divergence which cancels is the 0-point energy. So this is something that, as I said, also applies to the quantum field theory, but whereas here it's completely trivial, it's just plus 1/2 minus 1/2 is 0. In the field theory, I now get plus infinity equals minus infinity is equal to 0. So that's already much better. So we have vacuum energy is equal to 0. That's one. And the other is that some of the more sophisticated divergences of quantum field theory will also cancel. So for example, you have, if you look at scalar diagrams of this type, where you have a fermion running around the loop here, this thing will have a minus sign, plus, and then you have a bosonic contribution, which looks like this, say. And then, well, each of these diagrams is quadratically divergent. It will turn out that this is only logarithmically divergent. So this is all very nice, but also already you can see the problem here with this model, namely this degeneracy in particular tells us that all the superpartners have the same mass, and this is certainly not what we see in nature. In fact, the difference in mass between the particles we see and their alleged supersymmetric partners is quite large, certainly on the order of 100 GeV or so. It could even be worse. So this then is a problem that requires quite some thought. What you now have to do is you have to write these supersymmetric Lagrangians according to this idea which I introduced over there, namely start with a massless theory, then try to introduce some kind of symmetry breaking mechanism, and if you're sufficiently clever, the breaking mechanism will be such that this mass degeneracy between the supersymmetric partners is lifted. Well, I think this is all I can tell you. If I had another week, of course, I could tell you about interacting supersymmetric field theories, giving more details, but I think that is the point as well. And if you have questions now, please ask them. Yeah? You mean one of the higher, the extended supersymmetries? No, the chances are worse because n equals 2 is more supersymmetry. And as you can see here, n equals 1 supersymmetry just tells me that these two particles have the same mass, or that these two particles have the same mass. But if I now go to bigger supersymmetry, then the supersymmetry tells me that not just these two particles have the same mass, but these 5 particles have the same mass. So they're even worse off because there are yet more particles that have the same mass. So the problem of breaking supersymmetry and giving all these particles different masses becomes even worse. So that's why we content ourselves with n equals 1 supersymmetric models for the moment. Another problem with the n equals 2 models, supersymmetric models, is that they do not admit chiral fermions. Of course we need chiral fermions for the standard model. Now, it could be that in some superstring theory or some supergravity theory this problem is overcome. This is actually what we believe. But if you simply take these supersymmetric field theories as they are, without supergravity or superstrings or anything, then you're certainly stuck with this problem of chiral fermions. So that's why people hardly ever consider n equals 2 supersymmetric models. And since it's more symmetry, we would anyhow expect, if this symmetry is there, we have to go to yet higher energies to see it. So the first thing we're going to see, if there's anything at all, it's going to be n equals 1 supersymmetry.
Lectures, I would like to thank Professor Nikolai.